Hello students, in this video we are going to discuss question number 1 to 10 of MS Chouhan book, and the chapter is 5a, Alkyl and Aryl Halide Substitution Reaction. So this is a question number 1. As we can see, water is given as solvent. As water is a polar protic solvent, it is going to be SN1 reaction. As we know that polar protic solvent will facilitate the reaction which is SN1. So in this case, first if we start with the starting material, iodide is a leaving group, and in the step 1 this iodide would be eliminated. Okay, so we are going to have a carbocation in step 1, and as we know that the formed carbocation can rearrange itself to produce a more stable carbocation. Here we have one hydrogen which can give a rearranged carbocation by 1,2 hydride shift, and finally we will have this kind of carbocation. So after elimination of leaving group, we are going to have a carbocation, and this carbocation can rearrange itself to have more stable carbocation. And in step 2, water will approach as nucleophile, and we have lone pair over oxygen of the water, and it can approach this carbocation, and finally this kind of product is formed. As positive charge over oxygen is very unstable, minus of H plus will give the final product. So in this reaction, this alcohol will be the final product. The question asked that not expected to be intermediate. So in this case, B is formed, C is also formed as product, and initially we have D carbocation. So the answer is going to be option A. So in this case, the answer is going to be option A. This carbocation is not formed at all during the course of the reaction. Okay. So I hope this much explanation is much more. So we are going to solve the next question, question number 2. In this case, we have NaI, in which iodide is the nucleophile, and this is acetone. Acetone is polar aprotic solvent which facilitate the SN2 reaction. Here we have written in the question SN2 product we have to achieve, but if it is not written in the question, then also we can think about the SN2 reaction, because acetone is used as solvent here. Okay, so here we have Fischer projection. And Beer is the leaving group here. So in SN2 reaction, we know Walden inversion. In SN2 reaction, we have backside attack. So 100% inversion product is formed in case of SN2. So if initially we have this kind of molecule, and iodide is the nucleophile here, it can approach from the back side of this bromine, and this bromine will be eliminated from the system. As a result, the final product will look like this. The iodide will be attached over here. The hydrogen will come in this side because Walden inversion. This hydrogen will remain in the same position. This methyl will remain in the same position. There is no change for the position of ethyl. So this is a pure case of SN2 reaction where we have seen that inversion product is formed, and this structure is identical with option B. So B will be our answer. Okay. So we are going to solve the next question, which is question number 3. Rate of SN2 reaction negligible in which? So in case of SN2 reaction, there are many factors which can change the rate of the reaction, but we have to think that in SN2 reaction we need less steric central carbon. less steric central carbon, correct? Because we are going to have a penta-coordinated transition state. We are going to have a penta-coordinated transition state. This is not pentavalent, this is penta-coordinated nucleophile, and this is leaving group. So this is a general shape of transition state in case of SN2 reaction. So we have steric hindrance present around the central carbon atom. So we need a sterically free carbon. Okay. So all of these are cyclic. So there is a standard steric present in this molecule. But in case of C, this steric hindrance is much more than expected, because in this case we have 3 rings. This is ring number 1. This is ring number 1. If we think this part along with this is ring number 2. Okay, and if we think about this part, this is ring number 3. So we can think about 3 rings are fused using 6 carbon atoms. And here we have leaving group bromine. This cyclic part will look like a cage. Okay, it looks like a cage, and it is basically introducing a huge steric factor. As a result, nucleophile cannot approach from the back side. Okay, so nucleophile have to approach in the back side in case of SN2 reaction. This is SN2 reaction. So nucleophile should approach the leaving group from the back side, or Walden inversion must take place. But in this case, we can see that nucleophile cannot approach this bromine from the back side, as there is a huge steric hindrance present over the central carbon. And for another information, in this reaction, SN1 reaction rate also very less, or SN1 reaction also not possible. This is a very good example of a molecule where SN2 or SN1 reaction both are impossible, almost impossible, because this is a bridge head carbon. Okay, so this is a bridge head carbon. This carbon is bridge head carbon. In SN1 reaction, in the step 1, we are going to have a carbocation, and in this case we are going to form a bridge head carbocation, which is very much unstable. So in this molecule, we can say that SN2 and SN1 both are impossible. So the question was negligible SN2 reaction, and for this question our answer is going to be option C. Okay. So moving forward to question number 4. In this case, ammonia is the nucleophile. Okay, ammonia is the nucleophile, and we have 2 leaving groups here. One is this bromine, another is this bromine. So if you see the molecule very closely, then it is very easy to think about this kind of resonance present in this molecule. Okay, so if we want to write the canonical form of this molecule, we can write this kind of situation. This is possible, correct? So in this case we can have a double bond character. In this case we can have a double bond character, or a partial double bond character is present in the resonance hybrid. So we can obviously draw the resonance hybrid, and there is a partial double bond character developed on the resonance hybrid. So we can safely say that this bromine is a very bad leaving group. So this bromine is very bad leaving group. Okay, so this is not going to be substituted by ammonia. Now we have ammonia and another leaving group is present. So we are not discussing about this is going to be SN1 reaction or this is going to be SN2 reaction, because both case the reaction product will be same. So if you start with ammonia, the lone pair can approach, this is going to be substituted, and the final product will look like this bromine, or this conjugated bromine is going to be present, and along with this second bromine will be substituted, and finally NH2 will be attached. So in the question number 4, the option is going to be option A. Okay. So then the next question we are going to solve is question number 5. So DMF is used. Okay. So DMF is nothing but dimethyl formamide, which is a polar aprotic solvent. And in this polar aprotic solvent, iodide will behave like a nucleophile. Okay. So we are going to have SN2 reaction in this case. Now, if we closely look the molecule given over here, CH2, Cl, and this is Cl. So in both cases we have leaving group Cl present. Now, what about the SN2 reaction mechanism? SN2 rate is higher where the static hindrance is low. Okay, SN2 rate is higher where the static hindrance is low. So if we look closely, these two carbon which is directly attached with the leaving group is statically almost same, because CH2 and CH2. So both the carbon will have two hydrogen and alkyl group. So we cannot determine the rate using these two carbon. So we have to move forward and we have to look for the next carbon. So the next carbon from the right hand side is CH2 and the left hand side is C substituted by 2 methyl. So methyl are very statically hindered. Okay, so if 2 methyls are present, so this carbon, this left carbon will give a huge static factor, and for this reason the left hand side chlorine is not going to be substituted by nucleophile iodide. So in this case, iodide nucleophile can easily approach this carbon and the right hand side chlorine will be substituted, and the final molecule will be CH3, CH3, CH2, I. Okay. So according to the problem, the option B is the correct one. So option B is the correct one. Okay. The next question is, which of the following expression is representative of the rate law of SN2 reaction? So SN2 is nothing but nucleophilic substitution by molecule. So see, this is coming from the order of the reaction. Order of the reaction is 2. Okay. So the rate expression is rate constant K, concentration of Rx to the power 1, concentration of nucleophile to the power 1. This 1 plus 1, 2 is the overall rate of the equation. Okay. So these 2 is the overall rate of the equation. Okay. So we want 1 over electrophile, 1 over nucleophile, and option B is the correct one. So here we have 1, here we have 1. So this 1 plus 1 is going to be 2, which indicates the SN2 reaction. Both the concentration of electrophile and nucleophile are equal in the RDS. Okay. So option B is the correct one. The next question, question number 7, acetone and NaI. So acetone and NaI together will give SN2 kind of situation, because acetone is polar aprotic solvent. In polar aprotic solvent, SN2 reaction SN2 reaction favors, and the nucleophile present over here is iodide. Now, if we closely look this molecule, bromine, hydrogen, fluorine, hydrogen, and we have only 1 mole of iodide. So, we can say that we have two living groups, bromine and fluorine, or bromide and fluoride here, but iodide can substitute any one of them. So, the beta living group will be eliminated first. The beta living group will be eliminated first. So, if we see the living group property, then we can say that bromide is beta living group than fluoride. Okay, so in the class lecture we have discussed about the living group property elaborately. So, bromide is beta living group than fluoride. Okay, so this bromide is going to be substituted by iodide. Now, in case of acetone, we have 100% inversion product, which is known as Walden inversion. So, this iodide must be attached to the backside of the bromine or bromide. So, this iodide must approach from the backside, and this Br must be substituted. Okay. So, in the final product, there is no change in position for fluoride, but bromide will be substituted, and in that position iodide and hydrogen will be attached. So in this case the answer is going to be option B is the correct answer. Okay. So the next question is question number 8. Which of the following alkyl halide undergo rearrangement in SN1 reaction? So first we have to form the carbocation in each case, and we have to predict that it's going to undergo some rearrangement or not if it performs SN1 reaction. So, rearrangement is the cause, because in SN1 reaction carbocation can achieve more stability by rearrangement or ring expansion. So, in option A we have this carbocation. In this case, for the stability, we have only 3 hyperconjugations. Inductive effects are obviously present, but we are not introducing the inductive effect because hyperconjugation is present. If hyperconjugation is not present, then we can explain the phenomena of stability by inductive effect. Now, if we shift this methyl, which is known as 1,2-methyl shift, 1,2-methyl shift, we can have this kind of situation. Okay. So in this case, for stability, we have 3 hyperconjugative hydrogens along with some inductive effect. But in this case, we have 3 plus 3 plus 1, 7 hyperconjugative hydrogens. Hence, the stability will increase. So obviously, option A molecule, if undergoes SN1 reaction, there must be some rearrangement present. If we look option B, this carbocation is formed. Okay, after the elimination of chloride, this carbocation is formed. Again, it can rearrange itself by 1,2-hydride shift, and this carbocation is the final rearranged carbocation we are going to have in this solution. So option A and option B both undergoes SN1 reaction by rearrangement. It indicates the correct answer is going to be option D, all of these. But in this case, we must check option C, because there may be some mistakes present in any of the books. So after this type of elimination of living group, we are end up with this carbocation. Again, this hydride can shift by 1,2-hydride shift, and this type of carbocation is formed which can rearrange itself to form more stable carbocation. So there is some rearrangement, and the answer is going to be all of this option D. Okay. Okay. The next question is question number 9. Again, we have to go for SN1 reaction, but in this case, we have to give a order of reactivity, okay, or the rate order. So SN1 reaction rate is directly proportional to carbocation stability. Carbocation stability, okay. So if we look closely, the second option or the second molecule, after elimination of leaving group, we will have this kind of carbocation. So some resonance is present along with free hyperconjugation. So resonance and free hyperconjugation are the stability factor for the second molecule. If we closely look the option 3, after molecule 3, after elimination of leaving group, only hyperconjugation and inductive effects are present. We are neglecting inductive effects here. So we have 3 hyperconjugative hydrogen and 2 hyperconjugative hydrogens here. So we have 5 hyperconjugation here. This is 2, this is 3, and if we now solve the first molecule, so after the elimination of leaving group, the formed carbocation is only stabilized by 2 hyperconjugations. So the carbocation stability order is 2 greater than 3 greater than 1. So this is the carbocation stability order. And as we know that carbocation stability order is directly proportional to reactivity order of SN1 reaction or SN1 reaction rate. So we can safely say that option B is going to be the correct option. So last question in this video is question number 10. Which compound undergoes nucleophilic substitution with NaCN at the fastest rate? So here we can have some sort of confusion that what should be the substitution type we should think here. Is this SN1 reaction or SN2 reaction? Okay. So now the thing is, if we take SN1 reaction, then option D is the fastest reaction because more stable carbocation is formed here. And if we take SN2 reaction, the option is going to be A because less sterically hindered carbon. So we have to check one key word here, that is fastest rate. So we should have choose the fast reaction. Which reaction is going to be in faster rate? Because here we already know that SN2 reaction rates are higher than SN1 because in SN1 we have 2 steps, but in SN2 we have only 1 step. Okay, so SN2 reaction rates are higher compared to SN1 reaction. So here we have to check the rate by SN2 reaction, and as we know that in SN2 reaction we have to always go first for the less steric central carbon. In option A only we have carbon which have in bromine directly attached with carbon which have 2 hydrogens here. Obviously there is another alkyl group is present, but this is much far away from the central carbon. So the rate of the SN2 reaction will be higher or highest compared to these 4 molecules in option A. Thank you very much.